Oh, good evening, AP Physics students. Mr. Carson coming at you here, and today we're going to talk about magnetic fields produced by wires. So, this is problem 27 from chapter number 20, and it states, if I'm 25 centimeters from a wire, what's the largest current that wire can carry before it would produce a magnetic field as large as the Earth's magnetic field? Which is about 0.55 times 10 to the minus 4th Tesla. And you might be thinking, Mr. Kirsten, wires produce magnetic fields? I thought these little things called magnets produce magnetic fields. And it turns out, yes, anytime you have a current moving charge being carried in a wire, it produces its own magnetic field. If you've ever taken a wire and wrapped it around a nail, per se, and ran a little current through it and made your own a little electromagnet, you've seen this effect. So, and the way you can tell which way a magnetic field is being produced is notice the magnetic field goes around the wire, and it goes around the wire such that if you put your thumb in the direction of the wire and wrap your right hand around the wire, your fingers will point in the direction of the magnetic field, kind of as illustrated here. Now, we call this the right-hand rule, but notice it is a little different from our right-hand rules for charges moving in a magnetic field. Right? This one is talking about the magnetic field produced by a current-carrying wire. All right. So, and this is on page 562, so that's a good one to refer to if you get your right hand all confused. All right. Okay, so how much of a magnetic field does a current-carrying wire produce? Well, it turns out the magnetic field produced by a current-carrying wire is equal to mu naught over 2 pi times I divided by R, where I is the current in amps that the wire is carrying. R is the distance you are away from the wire. You guys know what 2 pi is, right? And mu naught is just a constant. It's on your equation sheets, and it's called the permeability of free space. And I know what you're thinking. You are saying, Mr. Kirsten, haven't we already studied that? Well, no, we haven't. What you might be thinking of, this is Tesla's times meters per amp. You might be thinking of epsilon naught, which is the permittivity of free space. Basically, you're going to use this a lot when dealing with I'll just write that down, permittivity, where this is permeability. This you're going to use in electrostatics when dealing with stationary charges. This you're going to use a lot when dealing with magnetic fields. And like I say, don't memorize them. They're on your equation sheets. Yeah, just know how to use them. All right. Okay, so this is our equation we're going to use here. And basically what we know is this is a constant. We know 2 pi. We know what the maximum magnetic field could be, a distance r away from our wire. We know r. And we just have to figure out the maximum current that this wire could carry. Okay? So again, here's a picture here. What we're thinking is, all right, I'm a certain distance away from the wire. I'm producing a magnetic field. What's the maximum this current can be for a certain magnetic field? Okay, so if I take this equation here and I rearrange it a little bit, solving for I would get I, the current, is equal to 2 pi times the magnetic field times R divided by mu naught, right? Just a little algebra there. And that is equal to 2 pi times the maximum magnetic field in Teslas. Remember, there's a couple different units for magnetic fields, Teslas, Gauss, a couple others, but we want to make sure we use Teslas, meters, and amps. good old SI units whenever we plug things into our equation so that everything works out. I see that pi cancels out here, and if we plug that all into our calculator and round to some significant figures, we get that the maximum current that wire can carry before the magnetic field gets as large as the Earth's magnetic field would be 69 amps, which is a lot of current. In my house, the maximum current that can flow through the house at any given moment is 100 amps. So that's a lot of current. All right, good job, physics students. We've got exciting times coming up here in physics. You know, today is February, the first video of February, and you know what that means? It means March is coming up. So in today's Discover magazine, I see here that 3/14 is coming up. And of course, you know, March 14th is a big day. Not only is it Pi Day, but it's Albert Einstein's birthday. What great stuff is going to go on that day. For instance, at Princeton, they celebrate Pi Day and Albert Einstein's birthday with pie recitals, pie eating contests, an Albert Einstein lookalike contest, and a no sock hop. All right, so check all that stuff out at PiDayPrinceton.com. All right, nice work, physicists. We'll see you tomorrow.